Hello everyone. This is a lecture on electricity and magnetism, where we'll be solving questions, okay, for your board exams. These videos are for any type of board like CBSE, CHSE, ICSE, anything. And we'll be solving questions that usually come in your board exams, final board exams. And, we'll cover everything. We'll cover all the syllabus. I had done it previous year also. Like some videos I had it in my playlist. You can check, but these are new videos, so probably stick with me. So we will be solving a lot of questions. Okay, and yeah, have your pen and paper with you. Don't just sit and watch the class. I hope you will involve yourself also in the class. That will really help you. Okay, so yeah, we'll be starting with electricity magnetism, and we'll complete the syllabus. Okay, we'll complete the syllabus, and yeah, all right. So let's start with a tricky part, and that usually students get tricked. That is your assertion and reason part. Okay, assertion, reason, MCQs, case studies. Those are the things that students sometimes get. You know, yeah, you know it. So let's start. So assertion, reason. The Yeah, you know the deal. So let's start directly. Okay. Assertion is an independent negative charge moves itself from point A to point B. Then potential at A should be less than potential at B. Okay. So this is the question. Let's start. Independent negative charge moves itself from point A to point B. Okay. So this is this one minus Q, suppose. It's moving from point A to point B. So then potential at A should be less than potential at B. Potential at A should be less than. That means VA is less than VB. So first of all, negative charge is moving itself from A to B. Suppose it was a positive charge, because we are familiar with positive charges. Suppose it's a positive charge. So if positive charge is moving from A to B, so what does it mean? It means that A is at higher potential and B is at lower potential. That's why the positive charge is moving from A to B. Okay. Yeah. We can also consider this as suppose the current. Current moves in the opposite direction of electron. That means in the same direction of the proton or positive charge. Right. So current will be moving in the direction of positive charge. So positive charge is moving from A to B. Current moves from what? Current moves from high potential to low potential. So here charge plus Q will be moving from high potential to low potential. So A is at a higher potential than B for which charge? Positive charge. So if it is a negative charge, what will happen? Just the opposite. If it is a negative charge, just the opposite will happen. VA will be less than B. Did you get it? Okay, I will give you another example of it. Again, the current example. Current is moving from A to B, from a higher to low potential. So electrons movement is in the opposite direction of current. Right? So electron will be moving from B to A. So see, B is your at lower potential and A is at higher potential. So eventually, negative charge is moving from a lower potential to a higher potential, which is correct. And so assertion is correct. Okay, potential at A should be less than potential at B for a negative charge. While moving from A to B, kinetic energy of electrons will increase. That's moving from A to B. Kinetic energy of electrons will increase. That's correct. It will increase. Of course, it will increase while moving from A to B, but uh, like it's not the reason for the assertion. Okay, it's not the reason of the assertion. So both statements are correct, but reason is not the correct explanation of assertion. So we can say the option B is correct. Will be the answer. Okay, I hope you got it. You get it? Okay. Okay, let's move to the next question. You first try to solve it. Okay, you can pause the video and solve it. Then only you see my answer. When two unlike charges are brought nearer, their electrostatic potential energy decreases. Two unlike charges are brought nearer, their electrostatic potential energy decreases. All conservative forces act in the direction of decreasing potential energy. Mm, when two unlike charges are brought nearer, suppose unlike, that means minus q plus q. Their electrostatic potential energy formula is what? U is equal to K Q1 Q2 by R. K Q1 Q2 by R, that is the potential energy. So when two unlike charges are brought nearer, that means minus Q brought nearer. So U is equal to minus Q square by R. Okay? Minus Q square by R. They're brought nearer. That means R is decreasing. So if R is decreasing, the thing is, um, there is another negative charge. If R is decreasing in negative terms, okay. Suppose again we will consider positive charges, because positive is the thing where our mind kind of works properly. It's when the negative signs come, our like mind starts to boggle down. So like, okay, suppose there are two positive charges. So potential energy will be k q square by r. Okay, suppose it was k q square by 20 centimeter or whatever. So now brought nearer, that means r is now 10 centimeter. So it becomes u dash is becoming kq square by charges won't change 10. So if you see, this one is actually greater than this one. So potential energy is increasing while we are like changing the distance between them. But if there was a negative sign here, okay, if there was a negative sign here, that means it had has it increased or what? Huh? It has what? It has decreased. Okay, this is minus 10 actually. Minus 10 is less than 20. So the whole thing has like increased or what? Decreased or increased? Okay, let me see. So you suppose this becomes what? If I multiply 5k q square by 100, you guess if I multiply 10 minus 10 kq square by 100. So kq square by 100, just forget about it. So the potential has gone from 5 to minus 10. So what? Eventually it has decreased. Yeah. So the assertion is true. Okay. Assertion is true. All conservative forces act in the direction of decreasing potential energy. That's correct. Again, that's all conservative forces act in the direction of decreasing potential energy. That's correct. But again, that's not the correct explanation for assertion. Okay, that's not the correct explanation for assertion. Okay. So again, option B will be the answer, because they are brought nearer. Damage the distance is decreasing. The thing is with the distance. It doesn't have to do with the conservative force act and direction of potential. Okay. Next question. Next question is what? Next question is at a point electric potential is decreasing along x-axis at a rate of 10 volt per meter. Electric potential is decreasing along x-axis at a rate of 10 volt per meter. So along x-axis it is decreasing. Therefore x component, okay, that means del v by del x decreasing at a rate of 10. That means minus 10 volt per meter, right? Decreasing. That's why minus negative. X component of electric field at this point should be 10 volt per meter per second. Let's see. So electric field is actually minus del v by del r, right? So it's a x-axis, so it will be E should be minus del v by del x. Ex should be minus del v by del x, and del v by del x is minus 10, so minus would be 10. So the answer is correct. Magnitude of Ex is del v by del x. Okay. The point electrostatic rates will decrease along x. Okay, this is correct. So the x component of electric field at the point should be 10 volt per meter. That's correct. So assertion is correct. Magnitude of Ex is equal to del V by del X. Magnitude. Yeah, this is correct. Um, yeah, the answer is right. It's option A. Okay. Assertion reason is the correct explanation of assertion. Magnitude it's saying that means Ex is equal to minus del V by del X. That's the formula that is used here. Okay. So this is option A. Assertion reason are true and reason of the correct explanation of assertion. Next question. Electric potential. I'm erasing this things. Okay. Electric potential on the surface of a charged sphere of radius r is V. It's a charged sphere, suppose a lot of charges are there. If a charged sphere of radius r, okay, is V. So electric potential on the surface of a charged sphere of radius r is V. Then electric field at a distance r is equal to r by 2 from the center. So at a distance r is equal to r by 2 is V by 2r. Electric field. Charge is distributed uniformly over the column. I mean, okay, let's see. From center to surface, electric field varies linearly with r. Here, r is the distance. On the surface, electric potential is V. Electric field at a distance r by 2. Okay. This question we have to do with this formula. If you remember, integration E dot dl is equal to what? Sorry, yeah, V is equal to minus E dot dl, right? If you remember, and the limit will be what? Limit is 0 to r by 2. Okay, so if we put the formula E, okay, E for the surface, for the whole surface is what? It is, um, it is what? KQ by r square, correct? KQ by capital R square. R is the radius, KQ by capital R square. Okay, charge is distributed uniformly over the volume. Alright. So here V is your V, yeah, and at this distance is actually V by 2r. So we can put here as V by 2r because up to r by 2 we are taking. So V by 2r is equal to integration E dot d. So I mean E is how much? K Q. Okay, Q is your rho dV your r square. Yeah, rho dV. Otherwise we can just take KQ by r square into, okay. This is the electric field of the whole surface into dl. Dl is the one we have taken the contour, that is 2 pi r. Otherwise we can just take um, dl. Yeah, dl is suppose dl sin theta is dl cos theta is 0. So dl integration 0 to I minus r by 2. So that will be simply r by 2. Okay. Just forget this minus 1. Alright. So um, otherwise we can also take it as 0 to small r. Okay. That one also we can do. Um, Otherwise no. A small r is eventually r by 2. So we just put it. So v by 2r is equal to this r are cancelled out, and this is kq by 2. So q by 8 by epsilon naught. 8 by epsilon naught. Alright. So This is a this is the expression for it, and V is equal to QR divided by, this is your 2 to cancel 4 pi epsilon. See, this is the formula after getting this. Okay, like after putting all this, don't think that R should be in below according to dimensions. No, no. This is as given in the question. Okay, so the thing is, we can do one thing. We can otherwise we can. Okay, we did what? Let me do now. Little bit win again. Okay, let me do it again. Okay, let's see. Okay, potential V is equal to, suppose V up to distance R by 2. Suppose we will calculate it. Okay, what I did was I did a mistake. I did a mistake. I have to agree. I did a mistake that I put it in place of, no. I don't have to put it. I have to calculate it as V by 2. If it is correct, then assertion is correct. Okay, my bad. Potential in the charge sphere radius R is V. Okay, so 0 to R by 2. This is E dot dl. Okay, E is what? E dot dl. Okay, so E dot dl, E dl, suppose E dl. So now electric field is how much? Charge is distributed uniformly over the surface. So E is K Q. Q is a what? Okay, K is what by 4 pi epsilon naught. Q is a what? Rho dV, yeah, by R square. Rho dV. Why? Because it's surface charge. Sorry, volume charge distribution over the volume. So rho dV by R square. Okay. So dV is what? dV is there. Rho dV. Okay. So what can we do here is rho into dV, right? Electric field rho into dV. And do integration for that. We can do an integration rho dV by R square. We can get a first electric field from here. So rho dV by R square, and volume of which part? Volume of volume up to R by 2 we need. We need up to R by 2. So 1 by 4 pi epsilon naught. Take everything out, rho by R square, and volume dV up to R by 2. Okay. So dV up to R by 2 will be what? 4 by 3 pi R by 2 whole cube. Correct? Yeah. So this kind of becomes 4 cancelled out. Then rho by pi epsilon naught R cube R square, and this 3 is here. Pi get cancelled out also. Pi get cancelled out. R cube by 8. Okay. So this is R square R. So pi R by 24 epsilon. Okay. So this is the electric field which we will put here. So 0 to this. Now let's do the potential part. 0 to R by 2. Rho R by 24 epsilon naught, yeah, into dl, like dl. So rho R by 24 epsilon naught, dl is what? Dl is your 0 to R by 2, that means simply R by 2. So we can say rho R square by 48 epsilon. Okay, rho R square by 42 epsilon naught. So um, V by 2 R, is it V by 2 R? We have to prove that. This is your V up to R by 2. Simply V would have been what? Let's check. Let's check for this electric field. For suppose electric field was 1 by 4 pi epsilon naught rho dV by R square. Suppose for the whole cube. Okay, V is for the whole cube, right? So 1 by 4 pi epsilon naught rho into 4 by 3 pi R cube by R square. Okay. This should have been for the whole cube. So 4 cancelled out. Pi pi cancelled out. R square R. So this becomes rho R divided by 3 epsilon. Rho R by 3 epsilon. Correct? Rho R by 3 epsilon. This is the electric field for up to distance R. Okay. Mhm. So for this potential, let's calculate potential would be what? Potential will be again E dot dl. So it would be what? EDL integration 0 to R. So EDL. Na? So rho R simply rho R square here. Rho R square by 3 epsilon R. So this is a V. Is this V by 2R? I don't think so. This is not coming V by 2R. Okay, so this is wrong. Assertion is wrong. From center to subject electric valid varies linear with R. R is the resistance. No, this is also correct. Okay, so both of them are wrong. Right? Yeah. Okay. So this is it for me. Erase it. Try to do yourself if you understood. Okay. Okay. Next question. Next question. Gauss theorem can be applied only for a closed surface. Yeah, that's true because Gauss theorem won't be able, we won't be able to apply it for a open surface. It has to be closed. Okay. Electric flux can be obtained passing from an open area also. Open surface. Mm, see, this is correct. And electric field can be also obtained. Yeah, electric flux. Okay, electric flux can also be obtained for this. Okay, but the thing is, Gauss theorem says what? Gauss theorem says E dot ds is equal to q by epsilon. From Gauss theorem, we actually try to calculate electric field. Okay, electric field through a closed surface. Any closed surface we try to calculate. For that, we need q enclosed. Okay. Q must be it must be enclosed. Otherwise, how will we calculate the electric? Okay. So, but for electric flux, we can always calculate electric flux for any open surface without the use of Gauss law. For Gauss law, we have to use a closed surface. Okay. So this statement is also correct. But the thing is, it hasn't mentioned Gauss law in the second one. Okay, so this is correct. This is also correct. But again, this is not the correct explanation for assertion. Okay. Yeah. So this is option B. I hope you got it. Gauss theorem will be for a closed surface. Okay, because Q enclosed by epsilon naught. We need phi. This is phi. Electric flux can be obtained passing from an open surface also. Yes, because E phi is also E dot A. From that we can calculate electric flux. But for that open surface, we won't be able to calculate Q enclosed by epsilon. Okay. Gauss law won't be applicable for it. Gauss law is for the calculation of electric field overall. Electric field. Yeah. So, statement of Gauss law says what? Surface integral of electric field is equal to 1 by epsilon of times of Q enclosed. So, eventually it is calculating electric field. So, option B. This is correct, but this is not the correct explanation of this one. Next, number 6. Number 6. Assertion. Okay, let's see. In the electric field, E is equal to in the electric field E is equal to this 4 I cap plus 4 j cap Newton per Coulomb. Electric potential at this is more than the electric potential at this. Okay, so let's check. Electron lines are already traveling high potential. This is correct. But let's check whether it's the correct expression or not. Electric field E is given 4 I cap 4 j cap. Electric potential at surface 4 0. 40 is more than the potential at 0, 4. Okay. So simple. At 40, the position vector is what? 4 I cap. At this point, suppose R1. This point, the position vector is 4 J cap. Okay. So if I calculate the potential for this point, it will be V is equal to V no minus E dot dr or dl anything. So minus E dot d E cap E dot dr is how much? 16 only. Minus 16. So this is V. V2 again minus E dot dr. Again if you see electric field 4j cap dot 4j cap is 16 only minus 16. So both are same. So both are same because the distance is kind of same. Okay. So this assertion is wrong. Reason is true, but reason is again not the explanation. So the option is D. Assertion is false, but the reason is okay. Yeah. Try the next one. Question number 7. You try this one first, then only I will solve it. Please try question number 7. Okay, done. Let's check. Two charges minus q are fixed at points A and B. When a third charge minus q is moved from A to B, electric potential energy first decreases then increases. First decreases then increases. Two charges here. Third charge minus q move from A to B. Okay. Electric potential energy first decreases. Okay, this one is kind of similar to the first question if you see. Yeah. So here if you see minus q minus q. So at this point, Okay. Suppose the distance is r. So at this point, potential energy is zero for at this point. At this point, potential energy will be what kq square by r for this charge system, right? At this point, if we take one this as the coordinate start point, reference point, so this is zero, and this is kq square by r. So eventually, it is going. This minus q is going from 0 to kq square, which is increasing. Okay, potential energy, increasing potential energy. Third charge minus q is moved from A to B. Now, third charge minus q is moved from A to B. Okay. So, the third charge will be moving. So, mm, along the line of joining, third charge is in stable equilibrium position of the center. If that's correct, it will be in stable equilibrium because the amount of force in this direction will be amount of force in this direction. So, forces will be cancelled out, it will be completely in equilibrium. So, this is correct. So, the thing is now about this one. Potential energy first decreases, then increases, then increases. Potential energy first decreases. Yeah, potential energy will be decreasing because it's going to a stable equilibrium phase. And at equilibrium, if you remember, potential energy is minimum. Okay, potential energy is always minimum at a equilibrium phase. So it is moving to a place where there is minimum potential energy. So see, this point is the equilibrium point. So it's like going there. So if it is going there, that means forget about these formulas. Let me explain. There are two charges here. Minus q, another charge coming, and this is the point where it is going to be maximum, the most stable point. Because see, this point will be repelling this one, okay, repelling, and this one will be repelling this one. Negative charge repel each other, so the forces will cancel out, and this will be a net force zero here. That means this point is a point of stable equilibrium. It will be at stable equilibrium. So this is equilibrium here at this point. So if it is moving towards the equilibrium point, that means potential energy is decreasing. Okay, and now after at this point, it will be starting to move away from the equilibrium point. Then it will be potential energy will be increasing. Okay, got it? Because the equilibrium position is the position of equilibrium position of minimum potential energy. Remember this. Very good question. Minimum potential, minimum potential energy. Okay. So when it is starting to move towards the equilibrium position, potential energy will decrease. But after it starts going away from the equilibrium position, the potential energy will start increasing. Okay. Yeah. Okay. Very good. So and also this is the correct explanation. So this is the option A. Very good question. Okay. Please write it down. Okay. Next question. Try this question number 8. Please try. Until you try, I will do it. Okay, so let's see. Number 8. A small electric dipole is moved translationally from higher potential to lower potential. Electric dipole is moved. Okay, electric dipole is plus Q minus Q. Translationally from higher potential to a lower potential. Okay, suppose 10 volt, this is 5 volts in uniform electric field. Okay. Work done by electric field is positive. Work done by electric field is positive. See here, potential is decreasing and this dipole is moved translationally from higher potential to low potential in uniform electric field. Work done. Work done means like change in potential energy, we can say, and change in potential is minus PE cos theta. Right? Minus PE cos theta. And if you see, there is a negative sign here, and it is going from uh, higher to lower potential. That means higher to low potential. So work done will be what? Work done will be decreasing. Like work done will be negative. Okay. Here work done will be negative, not positive, because U is equal to minus P cos theta. So this cos theta, forget about it. Minus PE. Okay. E is your positive, like electric uniform electric field is there. Dipole moment is there. So U is negative. Okay. U is negative. Yeah. So yeah, the Warden will be here negative. And when a positive charge moves from higher potential to low potential, Warden by the electric field is positive. Positive, yeah, that's correct. Positive charge will move from higher to low, then Warden is by the electric field is positive. This is correct, but the upper one is wrong. Okay? The very basic question. So option D, reason is correct, but assertion is false. Reason is true. In case of a charged spherical cells, ER graph is discontinuous while BR graph is continuous. Okay. According to Gauss theorem, only the charge inside a closed surface can produce electric field at some point. Um, ER graph is discontinuous. Charged spherical cells. Spherical cells, the inside part, it will be directly proportional, and outside it will be what, like this, right? So if you see, there is a break here. Yeah. Well, VR graph is continuous. Okay, VR graph. VR graph. How is VR graph? VR graph. VR graph will be always, I think, inversely proportional, completely inversely proportional. So that will be continuous. Okay, so this is correct. Okay, this is correct. VR graph is continuous. That's correct. According to Gauss theorem, only the charge inside a closed surface can produce electric field at some point. No, charge outside can also produce electric field because charge eventually produces electric field around it. Okay, it doesn't need a closed surface to produce electric field. It's just that through calculation, Gauss theorem says that charge must be enclosed to have some for calculation of electric field for a closed surface, charge must be enclosed. That is the explanation of Gauss theorem. But that does not mean that charge must always be enclosed. Okay, yeah. So this is wrong. Only this part is wrong. Charge can produce electric field like anywhere. Okay, here is a charge. So electric field is already there around it. Yeah, electric field is already there around it. Yeah, and yeah, this is option C. If we see along the axis of a charged ring, the magnitude of electric field is minimum at center. You try this one. I have done two questions. You try this one. If you see along the axis of a charged ring, the magnitude of electric field is minimum at center. Magnitude of electric potential is maximum. axis of a charged ring. Okay. So at this point, it's saying electric field is minimum. So that's correct. Electric field will be minimum here. Magnitude of electric potential is maximum. Okay. Magnitude of electric potential will be maximum. Yeah, that's also correct. V is equal to kq by r square. And electric field will also be electric field at the center is zero, right? Because it's a charge, all the charges are on the surface of the ring. So electric field at the center will be zero, but electric potential will be maximum with kq by r square. Yeah, this is correct. Um, Electric field is a vector quantity while electric field is electron. That's true, but like it's not the explanation for this one, is it? So this is true, but not correct explanation. So this is like what can I say? The option B. Yeah. Okay. So these were assertion reason questions. I hope these are very important because 4 or 5 marks are coming from here in board exams. So you should be prepared for it. Okay. So let's do some MCQ questions. Okay, objective type questions. Let's try. First is units of electric flux are. So this is like R is just like it's a mixture of units of voltmeter, square. So just one option. One option is correct. Okay. So see, tell me, let me know in the comment section. Answer the question. Try to answer in the comment sections. Okay. Involve yourself. Don't just sit and watch. Units of electric flux. So electric flux is simply phi is equal to E dot A. Yeah. E is your Newton per coulomb. A is your meter square. So Newton meter square per coulomb is one option. But this is coulomb square, so this is wrong. Newton meter square, this is wrong. Okay. So in case of voltmeter, we can also do because electric field is what del V by del R. That means volt per meter. So let's say volt per meter into area meter square. So that will be meter. So volt into meter. Okay. This is option C. Correct. Option C is the answer. This is wrong. Okay. Next question you tell me. Let me know the next question in the comment section. Please answer in the comment section so that I will know that at least you are watching and solving. Otherwise, there is no point of me just solving the questions because I can solve them. I don't have any problem. I have passed 12th class. I don't have any problem. You will have to work hard. Okay. A neutral pendulum oscillates in a uniform electric field as shown. If a positive charge is given to the pendulum, then its time period is neutral pendulum oscillates. Okay, pendulum doesn't have any charge. It's neutral and it is oscillating in a uniform electric field. If a positive charge is given to the pendulum, then its time period will be. See, there is a electric field lines going upwards. That means this is the high potential part. This is the low potential. This is the electric field going from high to low. Okay. Yeah. So high to low means the direction of positive charge. Okay. Yeah. The positive charge given to the pendulum, then its time period will become what? That is the question. The movement of positive charge, the direction of electric field, remember that. So that's the hint in this question. That's the hint in this question. So let's see. Let's try this question. So it's a positive charge given. So let's suppose positive charge. So this is the direction of electric field. So positive charge moves in the direction of electric field, right? So it will go like this, right? Because it's going positive charge going in this direction. Yeah, this is a low potential part. This is a high potential part. So it will go like this, yeah. And while coming back, it has to come back, so it will slow down, isn't it? Slow down. And again, while going up, it will go very fast, and again coming back, it will slow down. So eventually, if you see, the time period is increasing. Okay? Time period rather than a normal. In a neutral case, it would have just like you know like this. So now it is taking more time to cover the whole oscillation. So time period will increase. The next question. You write it down and go to the next question. Tell me this one. This one is easy. You should not be actually with this one. This one is easy. Well, very easy question. So two charges are there, Q1 and Q2. Okay. See, these are charge like line field lines are going into Q1. That means it should be what? It should be negative only. Q1 is negative. Field lines are again going into Q2 negative. And see, they are repelling each other, and there is no electric field in this part. That means this is a neutral. There is a neutral point here. That means all the field lines will be repelling themselves, and there will be no electric field line here at this point. So this is a what? Both are negative charge, both are same charge. Okay. Next question. Three identical charges are placed at corners of an equilibrium triangle of side L. If force between any two charges is F, they are equal to double dimensions of triangle. This is let's try this question. They're easy questions. Three identical charges placed Q, Q, Q. of an equatorial triangle side. Force between each two charges is F. F is what? KQ square by L square. What required to double the dimensions of the triangle? I mean, we have to make it 2L, 2L, 2L. So, how much work has to be? Now the burden is how much? Now the burden is F into L. So, to double the dimensions of the triangle, how much work has to be? This is a homework for you. Take it as a homework. Okay? Try this one. I won't be solving everything if I solve everything else. Please take a screenshot of it. I will solve this in the next class. Just take a screenshot and try at home. Next. Proton, deuterium, and alpha particle are accelerated through potentials of v, 2v, and 4v respectively. Their velocity will be a ratio. Okay. But proton E, deuterium that is E. Okay. Charge is E, right? Alpha particle 2 accelerated the potential v, 2v, 4v. Velocity will be a ratio. Velocity will be a ratio. That's right. See, kinetic energy half mv square is equal to qv. Alright. So suppose for mass, half mass of proton into Vp square is equal to E into potential is V. This is for proton. And we need velocity ratio. So Vp square is equal to 2 ev by mp. Correct? Alright. Now for okay, Vp will be what? Root over of 2 ev by mp. Now for deuterium half. Okay, mass of proton. Okay, mass of proton. Proton we will consider as hydrogen. Okay, so hydrogen H11. So proton mass can be 1. We can take the one. We don't need to take that one when it's asked this way. Deuterium half md Vd square is equal to Qv. Q is E. V is your simply 2V here. Okay. So half md mass of deuterium. Deuterium is H12. So 2 is the mass. Half into 2 into Vd square is equal to 2 ev. Okay. So Vd square is equal to half of cancel out 2 ev. So Vd is equal to root 2 ev. Correct? Yeah. Now, what is there left? 4v for alpha particle. Alpha particle again m alpha v alpha square is equal to 2 ev. Yeah. Like 2e into charge is 2e qv. Yeah. V is 4v. So 2e into 4v. So m alpha particle is He24. So charge is 2e, mass is 4. So half into 4 into v alpha square is equal to 8 ev. Right. So this is 2 cancelled out. So v alpha square is equal to 4 ev. So v alpha is equal to root over of 4 ev. So we just have to take the ratio now. So take the ratio root 2 ev and 4. So root 2 is to root 2 is to root 4, that is 2. Yeah. So if I divide root 2 everywhere, 1 is to 1 is to 2 by root 2. So answer is 1 is to 1 is to 2. I hope you got it. Okay. Please write it down. Okay. So done, we'll move to the next question. I will remove all this because you have understood, so please try to do yourself. Next, relative potential at a point P r distance away due to a point charge Q kept at point A is V. If twice of this charge is distributed uniformly on the surface of a hollow sphere of radius 4 r with center at OA, potential at P now is. Okay, relative potential at point P r distance away due to point charge Q kept at point A is V. Charge is kept at point A. Potential at P distance r is V. Twice of this charge distributed uniformly on the surface of a hollow sphere of radius 4r with center at point A. Twice of the charge is distributed. Potential at P now is. Okay, let's try this question. Try to see the hollow sphere part. Okay. So first, if we calculate potential V is equal to KQ by R. Okay. Now twice of the charge distributed. So V dash is equal to K2Q by surface of hollow sphere radius 4R. So, so KQ by 2R, which is your V by KQ by R. Very simple question. Nothing is there. Okay. Hollow sphere, there's just there to confuse you. So the answer is V by, right? Okay. Okay then. You take this number 7. Right. And number 7. Try number 7 and 8. You can also take them as homework. Okay. I will be doing this much for today. Take a screenshot of number 7, 8, and 9. Okay. Please take a screenshot. These are homework. And another question in the beginning. These are our homeworks. Please try and let me know in the comment section. Okay. Yeah. Okay then. Thank you for attending class and see you in the next class. Thank you.